2.0.0 Electrical Calculations. In this section, we'll use equations to determine various circuit values, explain how to use Ohm's law to solve for unknown circuit values, explain how to calculate electrical power. Various circuit values such as voltage, current, resistance can be measured to determine circuit characteristics. These values are related to each other. This relationship can be seen using basic math that you'll learn in this section. You'll also learn how electricity is generated and how to calculate power used. Defining circuit values. Again, if I said it before, let me say it again. When I say the word circuit, you think of circle because the electricity going out, leaving the battery, has to be able to return to the battery. It's going to leave on the negative and go through the switch, through the filament of light, make the light light up, and it will come back on the positive back to the battery. So there are the three parts of a circuit: the battery, the source, the load, and some kind of controlling mechanism. 2.1.1 Voltage. An electric charge can do the work of moving another charge using the forces of attraction and repulsion. The ability of a charge to do work is called its potential. When one charge is different from another, there's a difference of potential. The sum of the difference of potential of all the charges in an electrostatic field is called the potential difference, the electromotive force, or the voltage. This is a very important concept for you to get. Voltage does not move through a circuit. Voltage is a difference of potential. If you have a 0 volts, that's the earth. That's the earth we stand on, ground. And when every proton has an electron and they're paired up, everyone's happy. That is 0. There's a 0 potential. If you have a lack of electrons, you have positive 12 volts, meaning electrons are going to want to leave the earth and move toward that positive 12 volts. Current always flows from negative to positive external of the source. If you have a bunch of leftover electrons, you have a negative voltage. You can have negative 12 volts, meaning they are a lot more electrons than protons, and they will want to move toward Earth, toward 0 volts. The electricity is always going to want to move from a lower potential to a higher potential in the circuit. So it's always moving from negative to positive. Here, this is highlighted. It says the sum of the difference of potential of all the charges in an electrostatic field is called the potential difference, electromotive force, or the voltage. All three of those mean the same thing. Potential difference, electromotive force, voltage. It says figure 8 shows free electrons in a copper conductor. These electrons can be forced to move in the same direction by introducing a potential difference at each end of the conductor. The flow of electrons is known as current. Okay. All right, I'm going to take a little sidebar here. Let me see if I can. All right. I'll try to use my drawing skills here. This is a garden hose. I know that sounds a little ridiculous, but that's what it is. I'm going to fill this garden hose with marbles. We're going to put marbles inside the garden hose. And when I take a marble and I shove it in one end of this garden hose, on the other end of this garden hose, a marble's going to fall out. The garden hose could be 3 feet long or it could be a half mile. But if it's full and I push one in one end, an electron's going to fall out the other end. That's the same with electricity. We can think of these marbles as being electrons that move from atom to atom through a conductor. So if I change my drawing ever so slightly, I'm going to draw this as a wire. And what's going to happen is we're going to have, let's see here, what color do I want to use? I guess I'll use blue. This is the nucleus of the atoms of copper. There you go, these nuclei. And outside of those, we have electrons, okay? And they're rotating around in these shells. And here are all of my shells and all of the atoms of copper going through the conductor. And what happens is when we make this electron jump over to the next atom, there's an electron here that gets pushed over to this atom. And this electron gets pushed over to this atom. And it keeps doing that all the way through the electrical conductor until at the very end, there's a free electron and it's going somewhere. Well, basically, we'll take this end of the wire and bring it back around so that as we shove electrons in one end of the wire, the electrons are coming back to us. And then we'll pick them up and we'll push them back in. That's electricity, the movement of electrons from atom to atom through a conductor. Let me make this a little bit larger here. I'm going to make the nucleus of my atom. And I'm just representing this. That's a bunch of protons and neutrons. So I just do a little scribble like that. There's my nucleus. That's the nucleus of the atom. And I'm only drawing the valence shell. I'm not drawing all of the shells. I'm just drawing the last shell. And if it's a good conductor, it only has one valence electron in that valence shell. So it's very easy to knock that electron loose. It's easy to get rid of it. So here's an electron, and here's an electron, and here's an electron. And they all live in those valence shells. Like I say, when we get this one to come over onto the next atom, we knock this one loose, and it goes to the next atom. It knocks this electron loose, pushes it to here, pushes it to there. There are 6 ways. Now I have to use my memory. There are 6 ways to move electrons from atom to atom. We can use pressure. We can use heat. We can use light, chemical, friction, that's the one, and magnetism. Magnetism's the big one. Okay. So pressure, this is called piezoelectric. We used to have phonographs or stereo systems in order to play records, and the needle had a little piezoelectric crystal in it. And as the stylus moved in the groove of the record, the stylus would push on that tiny little piece of piezoelectric crystal, and it would cause electrons to flow. And then you use amplifiers to increase the amount of electricity until you get to a point where you have enough electricity to push the speaker, and the speaker gives you a sound. Heat, you can make a thermocouple, and it's 2 dissimilar metals welded together, and when it's subjected to heat, then electrons move. Light is photovoltaic, and that's your solar cells. Chemical is a battery. You use AAA and AA and C and D batteries. Friction is when you scrape your feet on the carpet, you touch the doorknob, and you emit an electrical lightning bolt. A tiny little electrical current flows from you into the doorknob and it hurts. And magnetism is the big one. Magnetism creates, well, at one time it was 80 to 90% of the world's electricity. I don't know what it is today, but uh, any generating plant that uses a generator, even a nuclear power plant, eventually they're using that steam power to turn a steam turbine that turns a generator. The generator is using magnetism in order to generate electricity. It's ways of getting these electrons to move, to leave their valence shell and move to the next shell. It's like a game of musical chairs. As you apply the pressure to those electrons move. When you stop, every electron's going to find a proton and sit down. So it's like musical chairs. And again, all of these different ways of causing this to happen are different forms of generating voltage, a difference of potential. So before I was talking about the fact that we have, this is a number line, and let's say that here in the middle is 0 volts, and let's say over here I have positive 12 volts and positive 24 volts, and let's say that this is negative 12 volts and negative 24 volts. Basically, to use a voltmeter, you have to have two leads. And the voltmeter, you'd put one lead, the black lead, here on the 0, and then you take the red lead, and I'm gonna try to draw an arrow like that, so maybe I can grab a hold of it and move it. So if you put your red lead here, it's gonna tell you 12 volts. It won't say positive, it'll just say 12 volts. And if you move this red lead to the second point in the number line, it'll say positive 24 volts. If I were to take this lead and move back here, it would tell me negative 12 volts. And basically, there's no such thing as negative electricity. The negative sign is just saying you're holding the leads in the wrong hand. In other words, this point is more negative in the circuit than this point. So you should have put the red lead over here, and you should have moved this black lead over here. And then it would say 12 volts, because this red lead is 12 volts higher than this black lead. So you can move these in the circuit and you can measure. Now that's going to tell me 24 volts, 36 volts, and 48 volts. It's a difference of potential. And I'm always cautious to say this because I know that as soon as I say it, someone's going to invent something to make me a liar. But I always say voltage meters have to have two leads because you're measuring the difference of potential between those 2 points. Current is different. You can use a clamp-on ammeter and you can read the amount of current. But a voltmeter has to have two leads. Like I say, I'm leery to say that because someone's going to prove me wrong as soon as I say it. Okay. Well, it says the unit of measure for voltage is the volt. In equations, voltage is often represented by the letter E, which stands for electromotive force. I'm going to highlight that. The letter E, which stands for electromotive force. In scientific terms, 1 volt is the potential difference between 2 points when 1 coulomb of electricity does 1 joule of work. That sentence is meaningless to us. We're electricians, not scientists. Basically, Voltage is the pressure that causes the electrons to move. The electrons moving is current, and the substance that they are moving through is resistance. It's like if you're running on a road or you're running in sand, you're doing more work to run through the sand because there's more resistance to your running. And that's what's happening with the resistance in the wire. Copper has relatively low resistance, but the filament of a light bulb has relatively high resistance. So as the electrons are pushed through the filament of that light bulb, there's a lot of heat loss, enough to the point where the filament of the light bulb will incandesce. It will glow because it gets so hot. And that glowing is what we want. We want that light. We want to light our room. It's very wasteful because we're also producing a lot of heat that we don't really need. So LED lights and fluorescent lights, they're more efficient. They cause less heat. So it's a better way to go. Supply voltage with a battery. Says there's a cathode, an anode, and a cell divider. Okay. I'm not going to get too much into this because I teach electron theory. I don't teach conventional theory. Note there are two theories on direction of current flow. Conventional current flow, where current flows from positive to negative, and electron flow, where electrons flow from negative to positive. This curriculum uses electron flow theory when discussing current. 2.1.2 Current. Current is the flow of electrons along a conductor. This is highlighted. It says the unit of measurement of current is the ampere, or amp. In equations, current is often represented by the letter I. This is because current was originally named for the French phrase intensity de courant by scientist André Marie Ampere, for which we have named the ampere or the amp. So current is affected by the following factors: the applied voltage, the wire size, the conductor material, the temperature of the conductor, and the length of the conductor. Okay. 2.1.3 Resistance. Resistance is the opposition to current flow. That's a highlight. Conductors have low resistance while insulators have high resistance. A resistor is a device that has a known specified resistance to current flow. This is highlighted. It says resistance is measured in ohms and is represented by the symbol R in equations. 1 ohm equals the amount of resistance that will limit the current in a conductor to 1 ampere when the voltage applied to the conductor is 1 volt. And resistance is affected by the following factors: the conductor length, the wire size, the material that it's made from. They go on to tell us that copper has a resistance of 12.9 ohms per circular mil-foot, and aluminum has 21.2 ohms of resistance per circular mil-foot. A circular mil-foot is a piece of wire that is 1 circular mil in diameter, which is 1/1000th of an inch in diameter, and it's 1 foot long. 2.2.0 Calculating circuit values using Ohm's law. Ohm's law states that the current in a circuit is directly proportional to the voltage and inversely proportional to the resistance. That's a highlight. So here's the formula. Current equals voltage divided by resistance. You'll see it written as I equals E divided by R. I like that equation more than the other two because it tells the true story. The current is dependent on both the voltage and the resistance. If you increase the voltage, you will increase the current. If you increase the resistance, you will decrease the current. It's inversely proportional to the resistance. It says, this is the first of Ohm's law, And it can be used to solve for current when both voltage and resistance are known. They give us an example. Suppose we have a voltage of 120 volts and a resistance of 12 ohms. What is the current? Well, the current is 120 divided by 12 equals 10 amps. Ohm's law can also be rearranged to solve for voltage and resistance. I know I have a lot of highlights here. This is a lot of important information, so I've got a lot of highlights. 2.2.1 Rearranging Ohm's law to solve for voltage. Suppose we know the current and resistance, but we need to find the voltage. To solve for voltage E, we need to rearrange the original equation. So we end up with an equation that says E equals I times R. That's the second of the Ohm's law equations. And the third of the equations is R equals E divided by I. Okay, so let's take a look at an example. If I'm going to draw a circuit here, and this represents the battery. This is how we draw the schematic of a battery. Those are voltaic piles. And then I'm going to come through a resistance, and I'm going to come back to the source. This is the negative side of the battery. This is the positive side of the battery. You know this is negative because this line is short and it's only long enough to draw a negative. But this longer line, you can snap it in half and make a positive out of it. So this is the positive side of the battery. This is the negative side of the battery. And the current is going to flow external of the source from negative to positive. It will come back to the positive terminal of the battery. The electrons will flow in a clockwise orientation. So if I said I have 6 ohms of resistance and I have 12 volts of electrical pressure, I can use Ohm's law that states I equals E divided by R. And I can calculate the current in this circuit. So we have 12 volts divided by 6 ohms, and we would end up getting 2 amps. 12 divided by 6 equals 2. Well, we said we can change the voltage. If we were to change the voltage, if this were 24 volts instead of 12 volts, if we increase the voltage, we increase the current. Current is directly proportional to voltage in an electrical circuit. So now we have 24 volts divided by 6 ohms, and that gives us 4 amps. 24 divided by 6 equals 4. So as we increase the voltage, we increase the current. Okay. Now, if we were to increase the resistance, let's see what would happen if we increase the resistance. Let's say we have 12 ohms of resistance. Well, 24 volts divided by 12 ohms of resistance equals 2 amps. So in other words, when we increased the resistance, we decreased the current. It's inversely proportional to the resistance. Current is directly proportional to voltage and inversely proportional to resistance. And I'm going to draw the Ohm's law wheel. We'll see that in a minute in the book. So here's my Ohm. That's a terrible drawing, but there's my Ohm's law wheel in which I'm going to put current and resistance and voltage. And the way you use this Ohm's law wheel is you cover, let's see here. Let me make a circle. That's good. And I want to make that circle solid. How do I make it? Let's see here. I'm going to make it a neutral color of blue. Let's see here. Let me change my properties. I'm going to make it fill effect solid. And I'm going to make this blue. And line style is going to be blue. Okay. All right. Let's see if that works. There. Well, it didn't make. Why did it not make it solid? Come on. Work with me here. Fill effect. Solid. Okay. And something tells me that I have to say okay. Well, okay. That'll work. That'll work. You can cover the unknown. If we cover I, if we say, what is current? Current equals voltage divided by resistance. The E is above the R, so it's voltage divided by resistance. And if we said, what is R? What's the resistance? We can find it mathematically by taking the voltage divided by the current. So here, if I said 24 volts divided by 2 amps, it would tell me that I have 12 ohms of resistance. And if I want to know what the voltage is, I can multiply the current times the resistance. 12 ohms times 2 amps equals 24 volts. So if they're next to each other, you multiply. If they're above, one is above, then it's a division problem. E divided by I equals R, or E divided by R equals I, or I times R equals E. Okay, that's how this Ohm's law wheel works. All right, let me go back. Let's see where there's their wheel. Okay, Ohm's law circle. To find current, cover current with your thumb, and then you see E divided by R. I equals E divided by R. To find voltage, cover the E with your thumb, and E equals I times R. E equals I times R. To find the resistance, cover the resistance with your thumb, and it's E divided by I. R equals E divided by I. Okay, very good. 2.3.0, calculating electrical power. Power is the amount of work being done. So there are different formulas you can use to calculate power. If you're lifting a weight a certain number of feet, you can calculate the amount of work needed to raise that weight, that height. We have our own power. It's the work being done by the electricity. So when that resistance, that filament of the light bulb, when current goes through it, that current is transformed from electrical energy into heat and light. Uh, it's converted. Some people will say it's consumed, but they don't really mean that. It's just a way of thinking about it. They say it's used up. It's not. It's converted. I guess it was Isaac Newton who said you can neither create nor destroy energy. You can only convert it from one form to another. So in that, the electrical energy is converted into heat and light. It's still there in the room. When you turn the lights out, the room doesn't suddenly become cold. That heat is still there. The power wasn't destroyed, it was just converted. But sometimes you'll hear it said wrong. Electricity is typically supplied from power generation plants. These plants use a variety of energy sources to generate electricity. They might use steam from burning fossil fuel. They might use solar, wind, or hydroelectric in a dam, or nuclear. Figure 13 shows how electricity is distributed from a generating station to residential, commercial, and industrial end users. So here's the nuclear power plant. Maybe they have a coal burner and they send that electricity up to 13,800 volts to your neighborhood where it is reduced. Actually, here it's being stepped up inside the generating plant. They're going to step it up to sometimes 1,000,000 volts. And it's sent down the power lines, and then in your neighborhood you have a substation that brings it back down to that 13.8 usually. It can be anywhere between 4,160 volts and 34,500 volts. And then in your neighborhood you have a pad transformer or the transformers on the pole that will change it from that 7,800 down to 240 volts for your house. So you have 120, 240. Commercial and industrial, they might use 208, 240, 480, 600 volts or higher. Sometimes they use 2300 or 4160. But in electrical circuits, power is measured by the watt. The power in watts equals the rate of energy conversion. So 1 volt pushing 1 amp through 1 ohm, there's 1 watt of electrical power. But it says to convert from horsepower to watts, multiply the number of horsepower by 746. In this, if we have 24 volts and 12 ohms, 2 amps, we have 3 ways of figuring out power. Power equals volts times amps. It also equals, here I should have drawn them at the same time. There are 3 power equations. We'll write all 3 of them here. Power equals the voltage squared divided by resistance, E squared over R. And it also equals I squared, the current squared, times the resistance R. So these are your 3 power formulas. You really need these written down somewhere. P equals E times I. P equals E squared divided by R. And P equals I squared times R. So in this scenario that we had before, I could say 24 times 2 amps equals 48 watts. 48 watts of power. So 24 times 2 is 48. I can say I squared times R. So 2 squared times the resistance of 12 ohms. So 2 squared is 4, and 4 times 12 is 48. Or I can say E squared divided by R. So 24 squared is, what is that, 576 divided by 12 ohms equals 48. Let me get my calculator. I want to make sure that I'm right. I don't know if I'm right about that. Come on, calculator. There we go. There, okay, so 24 times 24, 576 divided by that 12 ohms is 48. So there's your E squared times R. Divided by R. E squared divided by R equals P. Now I'm messing everything up. Anyway, so you have those 3 formulas. E times I squared times R, and E squared divided by R. Here, let me fix this. This is terrible. There we go. was trying to change color, and for some reason it wouldn't change color, but now we've got it. There we go, divided by R. That's your three power formulas. Okay, very good. To convert from horsepower to watts, multiply the number of horsepower by 746. That's the conversion. One horsepower equals 746 watts. 1,000 watts is referred to as a kilowatt, and 1,000,000 watts is referred to as a megawatt. I'm not going to do the conversion. 2.3.1, the power formulas. There's P equals I times E. And we can also say I equals P divided by E, and E equals P divided by I. But here is your power magic formula. P, I, and E. And you can do the same thing as the Ohm's law. You can cover with your thumb which one you're looking for. So I equals P divided by E, P equals I times E, and E equals P divided by I. Okay. And here is a large Ohm's law wheel that has 12 different formulas. They got these by rearranging the two Ohm's law and the power Ohm's law. They rearranged them and got these 12 formulas. So this is something very good to have written down. Put it on your wall so you can see it. 2.3.2, power rating of resistors. If too much current flows through a resistor, the heat created will damage or destroy the resistor. This is caused by I squared R heating. I squared R is one of our power formulas. So I squared R loss is actually a heat caused by using up the power in the resistor or in the wire rather than doing useful work with it. Where P equals the power in watts, I equals the current in amps, and R equals the resistance. Every resistor has a wattage or power rating which shows how much I squared R heating it can take before it burns out. For example, a resistor with a power rating of 1 watt will burn out if it is used in a circuit where the current causes it to dissipate heat at a rate greater than 1 watt. If you know the power rating of a resistor, you can find the maximum current it can carry by using an equation derived from P equals I squared times R. So R or I equals the square root of P over R. They're rearranging that formula to come up with I equals the square root of P divided by R. For example, let's find the maximum current that can be carried by a 1 ohm resistor with a power rating of 4 watts. So the square root of 4 divided by 1 equals the square root of 4, so it could take 2 amps. That's the maximum amount of current. I equals the square root of P divided by R. If this resistor conducts more than 2 amps, it will dissipate more than its rated power, causing it to burn out. Okay, and then going green. I'm not going to read going green. Let's see what else we have. 2.0.0, section review. Which of the following does not affect wire resistance? Well, the wire size does, the wire length does, and the material does. So B, the type of power. Find the applied voltage when the current is 30 amps and the resistance is 4 ohms. Okay, so E equals I times R, so 30 amps times 4 ohms equals 120 volts. 30 amps times 4 ohms equals 120 volts. Calculate the power in a circuit where the source of 240 volts produces 10 amps. So they want power, P equals E times I. So 240 volts times 10 amps is 2,400 watts. D. Very good. Let's move on to the next section.